Hello everyone, my name is Andreas Mendonca, and my colleague Yara Zbib and I will be introducing to you today our final project. Because of our shared interest in naval architecture, we aimed to create a completely parametrically designed pavilion that we have quite humorously dubbed the Whale. Somewhere between a pavilion and a barge, we wanted a hull form that could be optimized to improve fluid dynamics around the hull given varying viscosities due to saltwater density. Today, not only will we teach you how to construct a parametric hull, as well as a parametric pilot house and shading superstructure, but we will also show you how exactly we optimized our design utilizing computational fluid dynamics. In the slide in front of you is the base mathematical diagram of the parametric composition of the hull. Here we can see a visual representation of how mathematical calculations are derived in order to create the frame of construct points that define the closed NURBS curves. The result of the mathematical computations encased inside these grasshopper batteries is a digital formwork that comprises the domain of the lofted poly surface, which will ultimately become our baked hull. To construct a parametric hull, various parameters are given to a designated number battery. Depending on the parameter being analyzed, the resulting number battery is fed into the A input of a multiplication battery and multiplied by an auxiliary number battery holding fixed point values.
This gives us the base point matrix to construct our curves in three-dimensional space.
Some of the parameters are fed into a number battery that has a division expression computed within it. This allows these particular parameters to subtract from the resulting point in space.
The points that are being constructed are then fed into the V input of a NURBS curve battery. This allows a continuous closed NURBS curve to be constructed out of the vertices of each point in space. Once the curves are created, we now have our base framework for the parametric hull.
The curve output of each NURBS curve battery is fed into the section input of a loft battery.
This allows us to view the hull design as a mesh while simultaneously allowing the algorithm to flip and mirror the lofted polysurface along its longitudinal projection. From here, we can bake the model and obtain our parametrically designed hull. The deck and housing masses are constructed by extruding each plane's curve. Assembling lines along the final hull, each one is assigned to a script that constructs a catenary curve. The script uses a U-force in the Z direction, then uses springs and kangaroo to create a flexible curving geometry. Using divide on the lofted surface allows for a number of divisions on the surface. S-box provides control of the height of the division projection. Each set of geometry may then be projected onto the divided surface. Results from DIVA's climate-based daylighting factor analysis exhibits a difference in daylighting between each grid of the geometric design. The larger the grid multiplier, the smaller the daylighting factor is. When using Rhino computational fluid dynamics, the first step is to create the domain. The flow will be modeled within this volume. Next, we create an inlet and an outlet so that the fluid can enter and exit the domain with a specified inlet and outlet velocity at meters per second. The grid is assigned to subdivide the domain for a more accurate evaluation. The material is set to water. Then the simulation provides convergence information that can be visualized. A simulation run using Eddy3D illustrates results from a test of hulls against different velocities. In this project, we are trying to simulate saltwater density, so we decided to use a wind velocity simulation with different pressures to test multiple situations. The higher the variable input, the higher we assume the salinity levels of the water is, creating more of resistance of a flow against the hull. With a density variable, we were able to see how each hull may perform in different viscosities of salt water. Results can be seen in ParaView and in Rhino. Red indicates swifter motions, while blue represents more resistance. Renderings depict the whale in 3 different bodies of water throughout the world. That concludes our presentation. Please let us know if you have any questions. Thank you.